like Claire said, there is another workshop going on. So if you're not familiar with Noir at all, that workshop might be a bit better as it's getting started. It'll be with our excellent DevRel, Zé Pedro. Here I'll be going over a new tool that the Noir team is proud to announce, the Noir Profiler. So Noir Profiler is essentially a sampling profiler that is actually going to map your execution information to the source code. So you'll actually be able to see where your bottlenecks are according to call stacks. When I say the execution data, there's a few things here. There's the ASIR, so that's our intermediate representation that allows Noir to be backend agnostic. But then you need to be able to express basically your constraints and your execution with that respective backend. So that is the backend gates. And then we also have unconstrained execution, which is the ability to execute Noir outside of your circuit and then ultimately inject information back into your circuit. So I'm going to do a simple walkthrough of how you might actually use this profiler. So right here we have a very simple program. All we're doing is we're zeroing out an array past some dynamic pointer. Whenever I say dynamic, it means we have witness inputs that came from main. So we do provide some intermediate, simple ways to benchmark your program. We have Nargo info. It'll tell you some information. Okay, we have 24K ASIR opcodes, and when you see the Brillig, that is the IR for our unconstrained execution. So you see a couple also Brillig functions there. That's because we have some hard-coded in the compiler, very common unconstrained execution that we use to optimize things underneath the hood for you. So this is just a simple inversion and quotient. We'll go over that more later. But yeah, we need more information here, especially if we're gonna. That's a very simple program. What if we start to get to some more complex programs? So this is a very simple example of what the profiler would look like. If you're familiar at all with flame graphs, this is that. So you would run your command, and you would generate a flame graph that maps basically the ASIR opcodes that are associated with specific source code. So here we can see I've highlighted actually the memory operations that we get from that array write that we have. And that takes up right now the majority of our program, although we do have various other ASIR opcodes. Here's a simple GIF. If you're not familiar with the flame graph, you can click into your call stacks. You can explore it. This program is just main with a loop, so the call stacks aren't very large, but obviously this can scale up with larger programs. You can search using regex. I can search for the source code. I can search for the opcodes. This makes it a lot easier now to actually break down, where are the bottlenecks in my program. And then also quickly touch on that, yes, we also generate flame graphs for your unconstrained execution. When you generate with the previous command I just ran, you might see these other flame graphs here. We have these directives, which might not be as useful for you, but if you're starting to do some more advanced unconstrained execution and you're trying to optimize basically your witness generation, this might also be relevant to you. But for this talk, I'm mostly focused on just circuit optimizations and minimizing the amount of gates in your actual circuit. So here's a simple example of the Brillig one. You'll notice though there's no source code because this one is from our compiler, hard-coded, just a few opcodes in order to do, here we're doing a quotient. Yeah. So now let's actually optimize our circuit and look at what the flame graph might switch into. So we're going to use unconstrained functions. This is the ability to now exit our circuit and compute something outside of the circuit. If you're unfamiliar with unconstrained functions, I recommend going to the Noir docs where there's a primer on it, but I'm not going to be going over that here. So our original program we see now, let's instead mutate that array in an unconstrained function. So we've moved out of our circuit environment, and this is essentially, you could think of just normal execution. This is Noir, normal VM, just executing as you would expect for any regular program. And then inside of our actual circuit, we're then going to constrain what we expect that output to be. So we don't want to write in our circuit and do these expensive memory operations. So instead, we're going to say, okay, everything past that pointer has to be 0, and then everything else we expect to equal that original array that we had. We have to connect it to our original inputs or some kind of constant. There's some other things you can see here with how we require you to call on constraint functions. It's an unsafe block with a safety comment because you need to actually constrain it once you get back to your circuit. So here's an example of our now optimized flame graph. We no longer have any memory operations, which is what we want. And you'll also notice we now have 18,000 opcodes instead of 24K. This is pretty good. But we'll go over how this doesn't give us the full picture. Once again, here's them just side by side and how the opcodes look a little bit different. The flame graph looks a little bit different. And you can see now that the majority of our actual computation comes from just that comparison of the pointer. We also let you actually have like the backend specific information as well. So here we can actually supply a backend binary to our profiler along with the command that when the backend you were assuming has followed our API that is expected, and you will then be able to generate now the same kind of graph but with backend gates. So we can see actually the memory operations. For the Asir it was like 22% of our like total stuff that we had to compute. Here it's actually 66% because we actually have to do a lot more things in the back end in order to do these dynamic writes. So this is a large chunk of our program. This is our true bottleneck. So that same graph now with the optimized version, we can see we're from 65K gates to 23K. So this is actually a much larger optimization than the Asir showed us. And once again, all memory operations have been removed, and those the actual constrained part where we're just checking whether or not our array is good, it's actually only 8.6%. And you might notice though that there is all these range checks. This is because once again where it is important to have that backend specific context. We're using UltraHonk for this, which has lookup tables under the hood, and that's gonna. So all these range gates are using those lookup tables. So you're going to see a large chunk of the program is due to that. So sometimes once you start to get into the optimizing for the specific backend, you do kind of have to start to get the specific context there. So here's them just next to each other once again, and yeah, you can see how we got rid of those memory ops, which is what we wanted to do. So just to conclude, you're going to need both flame graphs to get a true picture of your optimizations, as every backend is going to implement these opcodes slightly differently. Groth 16 isn't going to have lookup tables for their range checks, and then now we have backends with World, and other people are implementing their own backends. You're going to need that specific context when profiling, and I think any backend actually should be able to just easily integrate with the profiler. It takes in a specific command, and if you follow the API and you're working on a backend, you can also integrate this tool for your own optimizations in your own circuits. You can use it now. It was released in our most recent release, beta 0.3 for 1.0, and then you can also go to the documentation, which has a lot of the similar stuff to this talk. If there's any questions about the profiler, feel free to shoot now. And that's it. Is there any questions? US what affects the proof? Do you mean the circuit size? Like the size of the program? That's okay. So he asked what affects the proof size in Noir. That's going to depend on your backend. When we were using UltraPlonk, previously, and other proving systems, they have a constant proof size. But ultrahonk actually it's linear, so or no, like logarithmic. It's like log n to your circuit. So it's going to grow with your circuit size as well. It depends on your backend. Yeah. So the other backends also will have, proof sizes that are different. So once you actually start to get to these optimizations, you are going to need more than just a seer and more than just the pure Noir program. Because as I showed you, it went from 24K seer opcodes to 18K seer opcodes, but that didn't tell me how much I actually optimized my program for ultrahonk. I don't know what it would be like in a different environment. Yeah, so the proof size is not dependent just on Noir. You're going to have to, if you are by fully integrated, it would assume that you also have, I guess, the profiler. You're following what we expect as input from a backend. There's specific format. It's not too complex. It's just if you're integrating a backend, when you add a certain seer opcode, you should also track how many backend gates basically you're adding. And that, if you integrate that gates command is what we call it, then you'll be integrated with the profiler. So the profiler for the backend gates, it'll take in a binary and then a command and then any extra flags that you might want for your command. So it just executes that binary, the backend binary. We compile down to a seer, which then can compile down to Plonkish or R1CS. So right now, the most supported backend is the one that Aztec uses, is ultrahonk, but you can integrate any backend that might conform to a seer. So there is other people who are working on, for their own means. WorldCoin is the most recent example. They're working on like a Spartan and Wur backend that follows their needs better than ultrahonk, which follows Aztec's needs. So it's backend agnostic. You mean like optimizing like the seer generation in Noir? Not yet. Yeah, we welcome it though. No one has tried to optimize our seer generation yet, but maybe there's room for that. Any other questions? All right. Oh. Yeah. Yeah, so the question was asking if I want to actually use my Noir program for multiple backends. Do I risk like optimizing for one and not optimizing for the other? Yes, basically. Yeah. Yeah, if you really want to use the same Noir program for multiple backends, it will be different, most likely. So even though Noir is backend agnostic and you can easily port something, like the context does matter once you actually want to get to proving. So, I mean, that's a general, I guess, it matters on your development cycle, I would say. But like, because if you wanted, this is once you're already getting to like optimizations and you're ready to productionize more. If we're just talking about prototyping, trying to work with a different backend, I think it's much more, yeah, you can port your Noir program to the Groth16 backend now and start working with that. If you want to start to get to, production optimization, this is more relevant because then you actually need to get your circuit as small as possible for your specific case. So yeah, if you hyper optimize your program for the specific backend, yeah, unfortunately it becomes less agnostic. But it could still be agnostic. It just might not be as efficient in the other version. It's similar with other backends in traditional programming as well. It's basically, what do you target? All right. If there's not any other questions, I'll be around though, and happy to talk.